you all once again for the FDP on robotic welding and welding automation. Now the second session is on hybrid welding and robot welding application by Mr. R. Nipin Shankar, Senior Marketing Manager, Lincoln Electric Private Limited. He has completed his BE Mechanical Engineering in 1996 at Madras University, and he have a total 24 years of experience, out of which 14 years in the field of welding equipments and welding automation. Nipin sir, the session is yours. It is visible, sir. Visible.
Thank you, sir. My voice is clear, sir. Can you hear me?
Yes, sir. Yes, sir. Perfect.
All right. Thank you, sir. And I would like to thank the organizers for providing me with an opportunity to talk about hybrid welding. To all of you, good morning once again and welcome all of you. My name is Nipin Shankar, and I basically am more into automation and recently in welding automation. But today, for a difference, I'm going to talk about hybrid welding. Hybrid welding is mostly misunderstood to be hybrid laser welding. Hybrid welding just means combining two different processes. So I'm just going to talk a little bit about hybrid laser welding, about twin wire MIG welding, and also about hybrid strip cladding systems. So before I start, I'd like to just give a small introduction about Lincoln Electric company. Lincoln Electric is a proud 125 years old company which was started by James and John F. Lincoln way back in 1895. We are celebrating our 125th year of existence this year. We are a pioneer with a market-leading technology. When I say we are a pioneer, we are in complete range of solutions. We started off first, that's different, but we exist in consumable equipment, automation, fume management, cutting process, and welding related accessories. We reached a $3 billion revenue in 2018, and we are growing. We have got a market cap of 5.8 billion, and as a NASDAQ listed company back in US, where our headquarters is in Cleveland, Ohio. We have 60 manufacturing facilities across 19 countries and over 160 distribution centers and 10,000 employees worldwide. Lincoln India, where I come from, is basically we started off in 1997 as a regional office with no commercial transactions. Subsequently, in 2019, we built our own manufacturing facility. You see on the screen, it's called it's in the Mahindra World City premises, and we are presently the largest single wire manufacturing facility. When I mean one particular factory's output, we are the largest MIG wire manufacturers across India, and we are the market leaders in MIG wire. We also import and sell equipments from our different facilities all across the globe, and we have a fully equipped training center, and we do around close to 250 to 300 to 270 crores every year's turnover actually. If you look at Lincoln global wise, we are the only 3 companies in the world that can cater to all categories, like from consumable equipment, gas products, automation, LICO, Colfax, and ITW. And in local language, LICO is Lincoln Electric, Colfax is ESAB, and ITW is Miller. So we are the only 3 companies across the globe who are in totally welding solution and can provide you anything. And we are, by last leg, we are the market leaders. We have a diversified business. Our business is not focused on particular segment or particular solutions. We lie across general fabrication, process, power, energy, heavy industries, construction equipment manufacturing, automotive, and transportation. So we have a solution for all ranges, and our business is diversified into a kind of 42% of our revenue comes from equipment and 58% comes from consumables. Normally, if you see any welding companies, they'll have a 30-70 combination, 70% coming from consumables and 30% from equipment, if it's a complete solution provider. But we are predominantly an equipment supplier with 42% of our business revenue coming in from equipment. And 60% of our business lies in America, which is North America and South America put together, and the rest of the world contributes to 30% of the revenue of Lincoln Electric. And we are the global leaders, and we are recognized as the welding experts, able to give you value and solution-driven products, and be it innovative products. There also we lay ahead. For example, we have kept changing with the IR industrial revolution. When the IR industrial revolution 2 came in, we were moving from transformer-based equipment and then wire and stick-based fillet materials. From where we moved on to inverter-based equipments and proprietary waveform technologies. When I say proprietary waveform technologies, I mean waveform controlled process, or kind of playing around the current and voltage over time to give a weld. What is this waveform? Is nothing but you play around with the current and voltage. When you're in a CV process, when you set the current and voltage, you allow the voltage to be constant, and the current is dynamically keeps changing. But the current and voltage need not be at that level always, because what is happening is heat is not required for welding all the time. So we play around with the current and voltage over time, and that's called waveform control technology. We have developed a lot of solutions. We started off way back in 90 with STT, which is a very famous process. Subsequently, we developed 100 plus. Each of these processes are developed for certain applications. So you have an end result. Based on that, you start working on a waveform. So that is why we have been innovating and providing automated solution. And with the latest industrial revolution, Industry 4.0, all our machines are Industry 4.0 compatible. We can when it's not just about collecting data and utilizing them, it's not an automated system. It's kind of autonomous system which we are moving to with our LW 4.0, which is a lean weld solution. So we are there all across the as and when the technology kept developed, we were with the forerunners. We are ahead of times. And if you look at Industry 4.0 and lean weld in India, we had been our factory is digital factory. We have got IoT installed, and all our wire drawing features in the factories are monitored through IoT. And we also support our customers with lean weld. When I say lean weld, it's kind of synonymous with increasing your productivity and reducing the welding cost. There's no point in able to increase the productivity of a customer if you're going to keep adding the manufacturing cost. So ideal solution or a lean solution comes in when you're able to increase the productivity and also ensure that you reduce the total manufacturing cost. That is what we focus on with our IoT solutions in India. So that's about Lincoln Electric. In general, a small synopsis. And now when we come to today's topic, hybrid laser, I would like to start with laser welding. Laser processing is basically what you call as heat generation. When we know what is welding, you need a heat source, and that heat source provides the heat required for melting the molten, making the base metal to molten metal, and then weld it with or without filament. If the heat source is a laser source, it's laser welding basically. So we have a laser source that focuses or brings into the rays into a focus point to get the heat generated, and that's how you do laser welding. So the intensity of the laser beam depends upon either the power, the source, the laser source, which is normally mentioned in kilowatts, or on the focus spot size. You can see here the focal point basically. It depends on the beam diameter and the focal length also. Based on that, your energy is developed. So based on the energy developing, the energy density and distribution in a focused laser beam, it also depends on the distribution of energy across the beam. Across, when I say the beam, the bead diameter. This is called transverse electromagnetic mode. This TEM. So you can have a pointed load like this, which is called a TEM00 or 00, and you have a cap-like, hat-like profile, or you have multi-mode. So these all depends on your focal. Then basically, to start with, the energy in the focused and unfocused laser beam is always the same. How do you concentrate and bring that energy to a focus point is how you decide whether it's going to be TEM0001 or multi-mode process. Each of them has got their own advantage, and they find specific applications. Like when you start with the TEM00, you start with a sharp pointed, where it is used for cutting, drilling, welding applications. I'll just go through this slide then. Here is it, single mode layer. This is called a single mode layer. This is best suited for, this is got a concentrated energy point actually. This is best suited for cutting operations, drilling operations, Of course, in welding too. And when I say remote welding, it's a non-contact type welding basically. And when you have a hat mode, it is also used in cutting and drilling, welding, but here, what is the end results that matters? Actually, you get wider weld beats when you talk about welding. Here, you're going to have a more focused weld beat. You've got to have wider weld beat. And you have to use a filler wire when you use this kind of laser applications. When you go to multi-mode, pretty much all type of laser beams can get you multi-mode, and this can be used in cladding applications because the energy is dissipated, actually evenly distributed. So you don't want too much penetration in a cladding application. So this could be ideal for cladding, heat treatment process, welding, brazing. Brazing is a low current process. You can use for brazing and also for additive manufacturing systems. These are some of the common multi-mode laser applications. The brazing, for instance, you see over here. The cladding application, cladding is nothing but overlaying basically, and then the heat treatment actually. So this multi-mode is applied across all these applications. This can be used for cladding application also with high deposition. In cladding, you don't talk about penetration, you talk about deposition and also about lower dilution. It can give you 16 to 18 pounds of close to 9 to 10 kilograms of material deposition per hour using a 6 kilowatt laser source. So laser welding basically is when a laser beam is focused into a spot, it is got enough energy to melt the steel, and that creates laser welds. It's a non-contact type process. When I say non-contact, in MIG weld, GMW or GTW, the electrode and the jaw comes in contact. It is a non-contact type welding, and it needs only access to on one side of the weld is required. There are many joint configurations that can be welded with this thing, and material gap can be filled with by adding additional wires actually. The advantage of laser welding is basically you get higher cycle time, you get higher weld speed, which means you can get higher weld speed. You have very minimal or no splatters, so less cleanup time is required. It increases the level of performance and reliability. So you have higher productivity in general. And as far as the quality part is concerned, it gives you consistent and reliably high quality welds actually. It's called a shallow, it doesn't have a deep, but a shallow heat affected zone, which means lower distortion. It's got precise control, and it's a closed loop with a feedback system, and it can be done in a stable welding environment. And as I said earlier, it's a non-contact process. So this is the advantage of laser welding. And autogenous laser welding is where you don't use a filler material. You can see over here, the parent material is melted, and then the weld joint is formed actually. The autogenous laser welding advantage is that you can travel at very, very high speed. When you talk about GMW welding, you're going to talk about 1 meter per minute, 1.5 meters per minute. Or when you do a manual GMW process, you're talking about 300 mm to 500 mm per minute welding. You're here in automated laser welding, autogenous laser welding, you're talking about 10 meters per minute speed on a 1 mm thick material. It's got lesser heat input, therefore lesser distortion, and it reduces the welding consumable cost because you're going to do autogenous welding without filler material. You'll have a deeper and more or less a narrow joint to have the weld done. So you'll have no consumable cost is involved in this. It's a very clean process, no spatters. So after welding cleanup is not required. It can weld dissimilar metals. And as I said earlier, it's a closed loop, so it's got a precise control, and you have an excellent quality monitoring system where you ensure that you get the desirable quality. So this is the advantage of autogenous laser welding application, but there are disadvantages too. There are some considerations too. For example, the initial equipment purchase cost can be higher than your conventional GMW or GTW or SMW welding machines. The input material has to be very high quality. Actually, it requires consistency, part of the part. It cannot have variation in its joint design. It cannot have gaps. All these will lead to poor welding qualities. So that's one disadvantage with an autogenous welding. And of course, the welding cost is also higher. We are working on process to reduce the welding cost. That's one part that Lincoln Electric's laser division in US, back in US, is working on. This can weld on different weld joints. All the joints configuration you see over here, it can do the welding on all these joint configurations. And I clearly told, I just highlighting the point that it should have lesser gap and it should have consistency in parts when you plan for laser welding application. So which means in basically the input raw material cost may go up if you want to have a consistency in quality. Whereas in conventional GMW welding, it sometimes foregoes. There are waveforms which sometimes foregoes, and it can compensate gaps and all those things. So that is, and the input raw material here has to be clean and oil free. Actually, it should be the case even with gas welding, GMW welding also, but here you need much cleaner surface actually. At Lincoln, we are doing non-contact type welding application. You can see a video of a typical job being done with a laser process. This is a company called Tennessee Rand, which is a Lincoln company in US. We have developed laser systems. We are also using laser for other applications. Like you can see a high-speed drilling application on this Coca-Cola can. You can see that almost almost 4,000 holes was done in 80 seconds. You can have a look at the video. So this was done with the laser process. It was done with a 300 watts laser power source. We are also working on hot wire laser process, which is basically for the cladding applications. It will give you low dilutions. When in cladding, your most important requirement is low dilution, low heat input, and you want higher deposition rate. So all this is possible with the laser hot wire process. So we have done a lot of cladding applications. You can see over here, the Tecaloy 625 consumable is used for cladding applications, hot wire cladding applications. So at Lincoln, we are doing a lot of development for the laser applications. We are not commercially yet entered in a big way, but all the developments have been done in the last 5 years. There's a specific team working on this laser welding applications, hybrid laser applications. So this is going to be laser being used in additive manufacturing. So basically, this is laser welding for you, and I'll now go to hybrid laser welding. Before going to that, I just picked it from the internet. Why should you go for hybrid and not laser? If you can see, it is all green here. There are some issues like the weld penetration, cracking pattern, all those things. It's a disadvantage with laser welding. So there are some cases where you would have to go with hybrid laser. For example, you have to have join dissimilar metals, and you want to have a alloying filler material that can strengthen the mechanical properties. You may need a consumable to be definitely used. In those cases, hybrid laser welding is proven to be a much better solution than laser welding. In hybrid laser welding, the only difference is you have a keyhole and you feed a wire using a GMW torch or a GMW power source. You separately feed a wire and melt it in the molten metal. That's called hybrid laser welding. It's faster than arc welding, but definitely slower than plain simple laser welding, or what you call as autogenous laser welding. This is slower than autogenous laser welding, but this finds more specific applications where you can implement hybrid laser welding. But it's much faster than conventional GMW welding process. It gives you lesser part distortion than the arc welding, because it gives you a much shallower heat affected zone, unlike the conventional arc welding machines. And they will give you what I call much better, deeper, wider penetration than the GMW process. Actually, it'll give you minimum spatter when compared to GMW process, so you don't have cleaning time, which is again a issue with GMW process. But there are ways and means of eliminating spatters in GMW welding. I think Dr. Murugan also addressed that in his presentation. But still, this will give you a much cleaner weld. It can easily weld dissimilar metals. It's more or less a control feedback closed system, so it'll have a much better control on your process, and it's got much minimal maintenance and process with a higher performance and reliability part of it. Pretty much all kind of weld joints can be done with a hybrid laser welding. You can do a cold wire laser or a hot wire laser with a hybrid laser welding. When you say cold, when you use a GMW torch and you feed a wire, conventionally it's called a GMW hybrid laser welding, where a combination of a laser arc with a GMW wire is being fed. Both these together melt the melt the base metal and then adds the consumable to fill up the gap, and that's how you get a hybrid GMW welding process. The heat affected zone is going to be definitely more than the laser welding alone, but it will be much less than the big GMW alone. It's often, it'll find extensive use in shipbuilding applications for heavy plate welding and where deeper penetration is required with huge weld joints actually. So this is the area where hybrid laser is applied. You can have hybrid laser with hot wire process where you can have the wire coming in preheated. So that means you have a much better deposition in comparison to a conventional hybrid GMW process. Much deeper penetration can be achieved also with filling gaps with a higher deposition part of it. Again, the heat affected zone is going to be lesser than the arc welding, but here it is not going to be more than the conventional laser welding, but it's going to be more or less similar to the conventional laser welding because of its hot wire capability actually. It's very good for welding materials such as carbon steel, aluminum, and aluminum to zinc welding also is possible. This finds extensive applications in places like cladding, where you need gap filling and welding, casting welding to be done. There and all you'll find wide applications for this hot wire laser. Similar to a hot wire laser, cold wire laser is the wire don't come preheated, so there will be much lesser heat here. The filler just enters into this and gets melted with the energy that's available from the laser source. A deep penetration can be achieved while filling gaps with this process also. A servo-driven wire feeder is separately given to feed the wire into this. The HAZ is similar to laser autogenous welding because it's absolutely a cold wire that's being fed and only the laser energy is coming in. So it will have almost the same heat in HAZ similar to a autogenous welding application. Only advantage with the cold wire over hot wire is that the wire welding power supply is not required here. In a hot wire, you need a welding power source to heat the wire or preheat the wire, which is not required here in terms of when you do a cold wire filling actually. This also finds use in cladding applications wherever gap filling is required and welding of casted parts is required. This again is a good process. When you compare the laser welding process, hybrid laser welding is preferred for stronger and deeper penetration welds on heavier material compared to autogenous laser welding process actually. Hot wire laser welding process has lesser HAZ compared to arc welding and has got lesser part distortion, and it can also allow you to weld a combination of thick to thin materials. It has been widely used in additive manufacturing. Lincoln has got a company called ColdJet back in US, which is making huge parts, which is done by additive manufacturing, and these processes are also employed there extensively for the additive manufacturing process. You also have laser brazing. Then you use a conventional laser wire and then feed the brazing wire to the servo drive wire feeder. That's called brazing. If in a copper wire based wire, that's called brazing. That's what is happening here. This will produce high quality joints with minimum HAZ and absolutely no distortion on the workpieces. No cleanup is required prior to painting. That is a big headache. Actually, you'll find a hybrid laser being used in critical applications. One classic example all across the world where hybrid laser is employed is during the welding the roof of the automotive cars. It could be Ford, Volkswagen in India, or any big players across the world. If you see, they employ hybrid laser for the roof welding applications. Laser brazing system is also used extensively. Laser brazing is actually used in the roof welding applications because it will give you normally after the welding when you can't have any cleaning process because when you paint or powder coat, there will be marks visible, which is not acceptable to unit high quality and high standards of workmanship. That is what hybrid laser and hybrid MIG brazing will help you achieve. So that is one advantage of hybrid laser and hybrid brazing application. I told you it's used on automotive visible class A surfaces. When I say what it means is that parts that is visible to when you see externally, the tail gates, the roofs, the C columns, all of these are more or less 100% built with the laser brazing process all across the globe. It's got very, very low heat input, absolutely no distortion, and make sure that you got a lower heat input, strong weld joints. They do very high-speed welding. The productivity, which is a concern for automotive industry, is handled here, and it's a very flexible process. And of course, it's a non-plasma process. That is one more advantage of laser brazing. Typically, where do you find laser welding and hybrid laser welding? It could be at autogenous welding, hybrid welding, either with cold wire, hot wire. They find extensive applications in industries like aerospace, automotive, large vehicle like heavy vehicle manufacturers, appliances manufacturers, nuclear industries do find a large application for the hydrogen fuel cells, basically, for the batteries applications. For the HVAC industry, you'll find extensive use of laser welding in all these areas, actually. Typically in automotive industries, you'll find it more in the body in white, power transmission parts, and the commercial ovens also. These are something where Lincoln has worked on, actually. The commercial ovens, the industrial fans, wind bands, seat frames, nuclear reactors, hydrogen fuel cells, cathode and anode assemblies. All these are some of the places where Lincoln has worked on in providing laser-based solutions, actually. And of course, the brazing will find a wide, extensive use in the body in white and the tailgate of the automotive cars. The C-pillar is also one particular area where normally brazing is used. Hybrid brazing is used. Laser hybrid brazing used. Here's an example of a transmission assembly where laser solution was provided. It was a 2 kilowatt to 6 kilowatt power source, laser power source that was used. It was developed by Lincoln's automation team, and it's been used for powertrain applications where you have we have two station systems where the operator keeps loading each of the station. We have laser hybrid welding being done here. Automotive seat application. Actually, like I was talking about the roof, one big challenge in automotive industries is the seat, because these are tiny parts and you need to be extra cautious of, because the user going to sit on that. There's load constraint also to be taken care, and these are very small, tiny parts with a lot of complex structures to be welded. So laser welding is found wide extensive usages in these seat assembly welding. Lincoln has supplied a lot of machines for the seat assembly welding, not in India but across the globe. This also finds application in seat assembly welding. One more example is welding a laser blank. You can see these two pieces. They are laser welded, and then they are then taken for the processing, the blanking operation. So it finds a lot of application. Nuclear assemblies is another application where we supplied an 8 kilowatt laser power source. It was a complete system with seam tracking, welding monitoring, taking out data to ensure the process. We are having process controls. So it's a complete closed loop system which we have worked on for the nuclear assemblies. Here is a conventional oven I was talking about. There are 3 parts to be welded. These are blanked, punched, and then welded. Please find domestic use, so it's got to be pretty good, neat, clean build, which was achieved with laser applications. Here we used a 2 to 4 kilowatt laser power source for doing this welding application with 3 robots that was doing this. Industrial fan housing is another example where we have laser welding solution was used. Again, it was a robotic system where the fixturings was developed, and one laser source was used for both cutting and welding applications. We had 2 robots, one carrying a cutting torch and one welding torch. So this is typical application where you can hybrid laser welding has been used. Fuel cell is another example where this laser welding application was used, and there are a lot of areas where hybrid laser welding finds its own usages. Actually, here's another example. So these hybrid lasers, they are advantages for the industries basically because they give very high travel speed, and they give you very deep penetration based on your requirement, and gives you lower dilution into base material, which means you have a shallow heat affected zone. You get the required strength, but you don't overdo the welding basically, because there's a limit to which you can control a GMW process. This process is highly controllable, and therefore you have a much better reduced distortion rate. Deep penetration welding is possible with hybrid laser arc welding. Can weld more than 2 times the speed of GMW, which means even if a very good process of GMW, you're looking at welding at 1.5 meters per minute, 1.6 meters per minute. You can travel twice the speed with the hybrid laser arc welding machine. You also have, you can do 100% penetration on square bed welds. It can also be used for blind and weld skid welds actually. So it finds wide extensive application. It is not yet been commercially used in a big way in industries, but it's slowly making inroads, and it's gonna replace a few, not everything, but few, like in India we are not there yet actually. We still have a lot of more than 60% of welding being done with stick welding or SMAW welding, which is the slowest, most inefficient process because you got to, but certain application demands these weldings. So there are still areas where we stick with the stick SMAW weldings. So our primary focus should be to move to faster and efficient process like GMIW, GTW, SAW. So laser is a long way to go, but there are a lot of industries in India which has already started. Like I was telling you, you will find this hybrid laser in all automotive industries for the roof welding. You go to Hyundai, Ford, Volkswagen, anywhere you go, you'll find them being used for the C-pillar and also for the roof welding applications. And the keyhole part of it allows you to weld with much lesser consumables. So your consumable cost comes down when you compare the process to a GMIW process. It's completely automatable. Like you can have oscillation done. You can have a hot wire, cold wire process. You can integrate it with a robot, with an SPM. So it's a completely automatable process as such, or in other words, it's an automatic process only. It's not a manual process actually. It's been used for sheet to beam welding also. Lincoln has used it for beam welding, what you call as the PEBs, or for the heavy beams with very high speed of 1.5 meters per minute for each side actually. So very high speed productive solution is hybrid laser welding. It can weld I-beams as I was telling you. Butt welds is possible, and you can travel from 1.5 to 3 meters per minute speed with full penetration from one side. There's something called OSW. You can do one side weld with 100% penetration is possible with hybrid laser welding. So that is hybrid laser welding for you. I just wanted to, because we have been talking about a lot about GMIW process. There are a lot of advanced GMIW process which we had been discussing about. Even Morgan sir was talking about the pulsed process, which has got a lot of advantages. Like you have specific application. If you want to weld a non-coated coated sheet, for example, zinc coated sheet is a big challenge to weld. When you're welding a zinc coated sheet, you need to have extremely good techniques and extremely good control over the welding. Otherwise, it is not at all possible to eliminate pinholes in a zinc coated plate or a coated sheet. So there is a minimum allowable limit set by the WPS actually, or your quality team will set the quality team will set an acceptable limit of pinholes in a zinc coated welded sheet because of the challenge that comes in. What is happening? All of us know that zinc vapors it tries to escape after the top material solidifies, so that it leaves a gap through which the gas vapor escapes, ends up in having blowholes or pinholes. So those challenges can be addressed by having a specific solution for that with a waveform and a technique to do that. Similarly, hybrid laser also has got specific application. Like hybrid laser is used extensively in cladding applications. It can be used on thin sheets. One classic example I am working on in the industry is the automotive two-wheeler tank assembly, where there's a big challenge. The rejection rate is huge. If you know the history, that actually it is normally done with a one-side coated sheet. At one time, Lincoln and India does not have a capability of making a one-sided coated sheet, so we need to import these sheets from Japan, or you need to use a two-side coated sheet, which means welding is going to be a big challenge. So there are a lot of rejections in rework. So laser could be hybrid laser one particular solution for this to reduce the rejection rate and rework rate. And we are talking about the automotive roof. One classic example where hybrid laser can be a solution. So this is finding extensive use in the industry. It's slowly and steadily replacing certain GMIW process, certain non-productive process with the high-speed productive solutions actually. So that's hybrid laser for you. If you have any questions on hybrid laser, I can take it on. But before that, I would like to finish. Since I started talking about hybrid laser, hybrid is nothing but combining two processes I said earlier. So I would like to talk about strip cladding also, which is also in overlay welding process, where also we have gone hybrid. So I'll just throw some idea onto this to you so that it'll be of interest to you actually. Strip cladding basically finds wide extensive uses in applications of that CP or critical process equipments in the oil and gas industries, petrochemical industries, the furnaces, the pressure vessels, the heat exchangers, the separators, all of them are special. They need to manufacture with special grade materials actually. But these are huge in size and subjected to severe conditions, operating conditions, which requires high level of reliability. For example, you need to have a base material which has got withstand impact toughness, which need to have good creep resistance, like the manganese or the chromoly, vanadium steel, things like that. Also, on the inside of this process equipments, you need to have water resistance, corrosion resistance, and high temperature protection, which is a slightly different characteristic for different materials actually, like the austenitic stainless steel, the nickel alloys, the monal duplex stainless steel, and all those things. So manufacturing all these things using one complete material may be very expensive. So what people have started doing is they have base material of one composition, and the inside where the resistance, corrosion resistance and all is required, they overlay or they pack it with a different material. That's called cladding actually. It's a bi-material cladding basically. So from the outside you'll have low alloy steel, and from inside you'll have special corrosion resistance alloy. So mechanical properties is taken by the outside one. So how do I clad it? The cladding plate can be done by either by roll bending or by explosive bonding, and they are stuck. Then they are fixed onto the inner wall of the pressure vessels. Another way of doing it is by welding overlay. That's what we are going to see now. Welding overlay cladding process actually. Initially, they started off with wire cladding because in welding we use MIG wires, submerged arc wires. So we started off with using wires for cladding. But you want to, you kind of want to lay over such a big area. It's going to be a time-consuming process. So people moved on to strip cladding, where instead of a wire, a strip. It could be a 30 mm strip, a 60 mm strip, a 90 mm strip, or a 120 mm strip with 0.5 to 0.7 mm thickness is used for is used to overlay on the inner walls of the pressure vessels actually. That's called strip cladding. Strip cladding, you can see some of the photographs. There's a ball valve, a lot of pressure vessel additions you see here. All these are cladded actually. Initially, it was done. Strip cladding was done with some. As I said, it started off with submerged arc process, wire process. Then they moved to submerged arc strip cladding process. Now we are moved to an electroslag strip cladding process, and the last one is the hybrid electroslag strip cladding process. Actually, this was way back in 60s. It was developed. In 80s, they moved to electroslag ESSC or electroslag strip cladding, and which is a higher speed than the submerged arc strip cladding. And then recently we got this 2016 hybrid strip cladding came. Now we look at strip cladding using a submerged arc process. The thing is that you need to have some fluxes on both sides, feeding from the front side and the rear side also. And the typical parameters, you're looking at 750 to 800 amps, 25 to 28 volts, and the travel speed can be around 100 mm to 140 mm per minute. That's the speed you can go. And the deposition rate usually is about 10 to 14 kilograms per hour. Dilution, which is very important, is 18 to 20%. And always you'll be able to lay a 2 mm thick layer. This dilution is defined by the penetration that you're able to achieve divided by the total weld height. In cladding, what you want is you want only the material to be bonded, not to be penetrating too much, because this has to be characteristics to take care of the corrosion resistance or thermal resistance on the inside of the wall. So you don't need penetration. So less penetration or less dilution is better when in cladding. So that is why you want to have a much lesser dilution when you do cladding applications. So here in submerged arc machine, you can get 20. When you do with wire, you're able to get 25 to 35% dilution. When you do with strip, you're able to get 18 to 20% dilution. And when you go to electroslag welding, you are able to get 7 to 12% dilution. So it's better you go from submerged arc strip cladding or SASW to electroslag strip cladding or ESSC. The electroslag strip cladding is revolutionized basically because it was able to do a much lesser dilution of 7 to 12%. It has moved from arcless process. It has moved from arc process to arcless process. It works on Joule's heating effect basically. So the flux feeding is also required from only one side. You would have seen in the previous slide, flux feeding is required on both sides, and arcing is done. Here it's not arcing, it's Joule heating effect that's come into picture. And there's some flux is required only on one side, and you can travel at with very high current of 1000 plus amps, even up to 1600 amps, with the same 20 to 22, 24 to 26 volt, and you can travel at very high speed of 1.6 meters to 3 meters per minute. You're looking at a deposition rate also to be more than doubled, 20 to 25 to 28 kilograms per hour deposition, which means more overlay per hour, and dilution rate is 7 to 12%, which means you get much better depositions basically. You can do a single or a two-layer process with this electrostatic strip cladding, and you get a clean chemistry when you do with an ESSW process rather than with the SASC process actually. So that is the advantage of electroslag strip cladding. Now I'll come to the hybrid part of it. Why do I call it a hybrid electroslag strip cladding welding application? Is I have the same flux being felt on one side, I have got the same Joule heating effect, but I introduce an additional metal core wire, maybe one wire, maybe two wires, into the heat zone, into the hot molten material, and the metal core wire takes heat from this, melts and deposits more. So you got a higher deposition for the same current range, and you're going to deposit 32 to 42 kilograms per hour based on your parameter setting. And you can use 60 mm strip. In addition to that, you can use two 1.6 mm wire metal core wires. Metal core wires will give you much better, higher deposition than solid wire. You know that. So this is directly giving you this hybrid cladding application by introducing two metal core wires. Additionally, is increasing your deposition rate by close to 25 to 30% more than that basically, and it has got a good low dilution level, and it still is able to give you clean chemistry. Also, this metal core wire will give you an additional benefit of adding any additional material composition you want to be added to provide higher corrosion resistance, higher strength, whatever is required. So this can be done by adding a metal core wire to the strip cladding process. So that is what is called as hybrid strip cladding applications. But when I make it hybrid by introducing a metal core wire, I increase the deposition rate, B allow to make higher, thicker cladding or walls, and C is that I can strengthen, I have the higher strength, mechanical strength by adding additive materials into the metal core wire. Metal core wire composition can be designed as per my requirement, and it has got all the other benefits of electroslag strip cladding applications. So that is hybrid electroslag strip cladding application for you. You can see a photograph of here. This is a strip that's being cladded, and there are 3 wires fed here. So you can feed 1, 2, or 3 wires and make it much more effective. So that is hybrid electroslag strip cladding application. Now, when we come to the metal core part of it, hybrid metal core part of it, what are the advantages by adding? It can compensate loss in alloying elements by adding alloy elements to the metal core wires. So this will take care of the chemistry of your end weld thing, and will give you a higher current. Metal core we have decided because metal core give you a higher current density than solid wire, means it requires less energy to melt, and we are not preheating it. We are picking up the heat from the strip clad itself to deposit. It absorbs weld cool energy, helps to control the heat input, dilution, and weld puddle. It will enter, the metal core is fed into the hottest part of the strip, and it does homogeneous weld deposit. Hot metal core via addition to the molten metal increases deposition rate substantially. It also introduces flexibility in achieving stringent weld chemistry in thinnest possible height by adding additive material, whatever alloying element you want, you can use in the metal core wire. So that is one successful application that Lincoln has used, the hybrid electroslag strip cladding application. This is a GR22 reactor, which is cladded with the hybrid process in Italy. Here is a 347 cladding material where cladding was done with the hybrid electroslag cladding applications actually. Here we used a 90 mm strip, 0.5 mm strip to deposit 3.7 mm over is the overlay height. Actually, that's deposited. We also have developed this for smaller diameter cylinders to do the inner walls of the smaller diameter cylinders. The ESSC with hybrid technology has been used in those applications too. So in summary, the ESW, the electroslag welding, is the most used strip cladding process for critical pressure equipments or the CPEs fabrication. ESW can offer you a single layer high speed solution for many commonly used alloys. By adding the hot metal coat wire to the ESW well poured, it offers various benefits including lower dilution, higher deposition rate, and higher speed. The hybrid ESC achieves much stringent cladding chemistry, which makes it much better to use these kind of solutions. It gives you flexibility in cladding. It allows you to easily achieve your desired cladding chemistry and cladding thickness without changing the strip chemistry and cladding flux. This one thing has given Lincoln an advantage of allow you to use one single flux for any applications. The flux is common for any of the ESS application you want to use. You don't have to maintain different flux for different material composition. No, common flux. That is done with this solution actually. That's the last point I was trying to explain. And here is a photograph of the cladding head. This is conventional 2D. We call it the 2D cladding head or the two-dimensional cladding head, where you have magnetic steering kit and you can feed the strips and then do the welding. Here is the additional wire feeder, metal cord wire feeder, which will feed the wire into the molten area to pick up energy from the overlay and then deposit the metal cord wire there actually. So this is the 3D cladding one. In addition to the 2D cladding, we have a separate metal core feeder, and the rest of thing is taken care by the power source and the electronic control part of the machine. So this is hybrid laser welding for you. Then I finished my second topic. I was addressing on hybrid laser. I was talking about hybrid strip cladding. Now this is called a hybrid thin wire welding, but basically this is a conventional GMW process special. I'll tell you why. When we are doing welding, our main focus, as I told you when I started, is we focus on lean management, which is depositing more by reducing the deposition cost or the manufacturing cost. So when you look at means and way of increasing your productivity, people normally talk about using higher diameter wires. For example, if I'm welding with a 0.8 mm wire, if I move to 1 mm wire and I move to 1.2 mm wire, I can move to 1.6 mm wire. That is where GMW ends. But people have started using, some customers, some industries have started using 2 mm wire for GMW process. They assume that by increasing the wire diameter, you will deposit more. The other way is to have two wires together welding in one single arc. This is multi-wire systems. So these are ways and means of increasing deposition. But Lincoln normally looks at what is the most cost-effective way of depositing higher. Now I want to address the general perception that people have is, it is true that when you're depositing using a 1 mm wire and a 1.2 mm wire, your 1.2 mm wire will deposit more. It is not true always. So it is not just decided by the wire diameter. The deposition rate depends on various factors. Like you can see this, it's a kind of stability you have to bring. You should have an arc, stable arc. You should have a consistent or more or less stable travel speed and stable wire feed speed. It is not that you increase your wire feed speed, you can just keep on increasing your wire feed speed and keep on increasing your travel speed, keep on building. You will lose your arc stability. You need to have a perfect balance in all these three. Only then you will be able to get a good weld. So moving from smaller diameter wire to higher diameter wire does not guarantee you higher deposition. It needs you to take care of the stability of these process, the parameters, the wire feed rate, the current, the travel speed, and the arc stability. And also when you move to higher diameter wire, this become it's less tolerant to poor fit-up joints, which is not the case with thinner wires actually. And your current density will only decide the deposition rate. So increasing the current alone will not help, increase the wire diameter will not help. We have done a study in our Lincoln Weld lab to see what are the effects of increasing current and voltage and travel speed and wire feed speed on a process and see how stable it is. We found out that until certain range, until certain current, it's better to use a 1 mm, 1.2 mm wire. When you cross a transition level, it's better to move to a 1.4 mm wire. So when is the transition level that comes when I can use a 1.6 mm wire was ruled out because 1.6 mm was not able to give me the best result when I'm doing manual welding. In our robotic systems, yes, that we have to again do the trials and decide. So we decided that when you're going to do a manual welding, and also to some extent you on robotic welding, it's always better to use a 1.4 mm wire to give you the optimum deposition. I'm not saying the maximum deposition, I'm saying the optimum deposition. Means good quality weld, required mechanical mechanical properties, penetration, quality parameters, everything meeting, and you have a higher speed. So optimization comes at 1.4 mm for manual process. That is what we studied. So this made us realize that increasing the wire size is not the only solution. The other way of looking at increasing deposition is having two wires in the same arc. You have heard about tandem MIG. Tandem MIG is a process that has been extensively used now in a lot of industries. All the earth moving manufacturers like the JCBs, the Caterpillars, they're all started using tandem MIGs. Their tier 1 suppliers have also moved to tandem MIGs. It means two power sources welding at the same time in a single puddle, which means there are two power sources, two wire feeders, two contact tips, two liners, two arcs, but one single weld puddle. How this will help you is to allow you to deposit more than what you can do with a single wire system and increase your productivity. This will give you exceptional travel speed as high as 15 kilograms per hour if you want. It will also give you reduced heat input because it allows you to travel at very high speed and also gives you superior weld quality. At Lincoln, we have developed two types of hot wire tandem process. One is called a synchronized tandem and a hot wire tandem. In synchronized tandem, both the wires arc and melt one after another in tandem to give a good stable arc. And in hot wire tandem, only one wire will arc, the other one will only be hot wire feeder kind of solution where you have but you still use the two power sources there to give these are both of them find extensive application in their own region. For example, if you want to manufacture build a small diameter shell, if you're using tandem and if you're rotating at a very high speed, your weld puddle will tend to flow over. So before it freezes, it tends to flow over because you're rotating the job. So there, it's better to have less heat input. You can use a hot wire tandem. So this is tandem process increasing productivity. Now, can tandem be used all the places? No. Why is that? I'll tell you. Because tandem does not find extensive application for various reasons. Because when you have two arcs happening in the same weld puddle, you need to have an extremely good feedback system to make sure that there is no arc interaction or magnetic arc blow which will affect the quality of the weld. The torches are special torches, so the parts are expensive, so therefore the running cost is going to be high, and also the tandem torch is little bigger. It cannot reach all joints. It has got a constraint. You can do on a different level, but not at a you cannot have sharp bend, sharp corners where your tandem torch will not be able to reach. You cannot do it on a smaller diameter pipes where the material will tend to flow over. So and also it is going to be very expensive because you're going to use two power sources, two wire feeders, all two with a special torch and a special controller. So it's not going to be twice that of single wire system. It is much more than that. So that is why there are a lot of limitations comes from tandem MIG. So Lincoln was thinking on developing a hybrid process. What I mean by hybrid process is I want a machine that can give me the deposition rate of tandem MIG, but not as expensive as tandem MIG, or also with not so much complexity that comes with the tandem MIG. That is how Lincoln developed something called the Hyperfill process, removing all the complexities involved in tandem MIG welding. So it is a hybrid process between the single wire and tandem arc process, and is the first ever process, twin wire process that could be used for robotic and manual welding applications. increases the deposition rate of GMW process more than twice, makes it simple for operator to manage the weld puddle, which has been tested and proven, and also it minimizes the setup complexity that comes with the tandem set. So where you have difficulty in terms of process or in terms of commercial viability, Hyperfill is a solution. How is Hyperfill a hybrid process and different from tandem? Because it's got only one single power source, single wire feeder, single torch, single liner, and single contact tip. Not just that, it's got only single arc. But it gives you 2 wire deposition, which means 100% increase in efficiency of deposition. That's called Hyperfill process for you. I'm just showing this small video. You can see here there are 2 wires actually, but there's only 1 arc. Even though there are 2 wires, there's only 1 arc. Excuse me. And you can see it's a much wider arc in comparison to a conventional single wire MIG process. So that is Hyperfill for you. It's an advanced high deposition process with more suitable, stable, dual wire, single arc weld. A waveform, it's a waveform dependent. You see a liquid bridge will connect both the wires and it will allow you to deposit one single weld puddle, one single arcing and one single droplet, but it will give a wider cone with a deeper penetration and takes care of good weld qualities actually. How is it different from hybrid or different from a conventional MIG wire? There's a small change that has been done. Just a second, sir. Here you see on the drive roll part, there's a small change. Where you're feeding the wire, there's a small change, and the contact tip, there's a small change. Otherwise, it's as simple, with no complexities as a single wire system. And in a tandem MIG, you have a lead arc and trail arc. You have different parameters for lead arc and trail arc. Both of them have got their own task cut out. But in Hyperfill, you don't have those things. You can weld in either directions. The orientation does not matter. So with all complexities of tandem removed, it gives you high deposition at part with the tandem process, hybrid GMW process. If you look at the process capability part of it, it's used for both manual and robotic application. It can deposit up to 12 kilograms of weld per hour. It can increase your deposition rate by 100% compared to a single wire process. There's no implementation risk, unlike tandem. It's got a much lower capital investment compared to a tandem process. It's easier to maintain. It's got less spatters, which means you get a clean weld, and you can do 8 mm fillet in one single pass. When you look from the automation capability, it is compatible with all robots that you get in the market. You can do it with 2 1 mm wires or 2 1.2 mm wires. You have torch available for all models. You have scene tracking and touch sensing available with this process to support you. When you look at the capital investment part of it, it costs almost as much as a single wire system, but it will give you deposition at par with the tandem MIG position, which means it's 50% lower than tandem MIG in terms of investment, but 50 at par with the productivity part of it. That is Hyperfill process for you, and this is an all-round process. It can give you a good quality, very high speed, high deposition, and also it takes care of the quality parameter like the penetration, no spatters. So it's an all-round process which can be extensively used for applications. Lincoln's power control technology is used for implementing this Hyperfill hybrid process actually. Some of the examples, here's the hybrid process that's used for mining buckets. Earlier, it was done with 9 passes using one metal coat 1.2 mm wire. By implementing hybrid process, they were able to do it in 5 passes. So they produced 4 passes, and the original arcing time or the welding time came down from 1,000 hours to 600. This is a huge mining bucket. 1,000 hours of welding, it was reduced to 600 hours basically. 40% reduction, but 400 hours of reduction. Here's some other photograph of the same mining bucket. It was also used in hydraulic ramps you see over here. It reduced the welding time from 30 minutes close to 18 minutes actually. So we have done it in India also for a customer. We are developing it actually. It has been used in mining trucks, not just the buckets, but also the truck bodies, with a semi-automated linear welding track and a trolley. Hyperfill was able to do at around, it allowed the customer to move from 3.3 meters per minute speed to 0.5 meters per minute. You're looking at depositing 8 mm, 12 mm fillets. Okay, it's not small welds, it's huge welds they're talking about. On a pipe welding application, arcing time was 8.5 minutes. It was reduced to 2.7 minutes by moving to a 1 mm hyperfill process. This hybrid hyperfill process is also used in structural welding for 1G, 1F, and 2F applications for manual and robotic sites. Here's another story of an offshore job component where initially they were doing 7 passes with flux core arc welding, which we moved to solid wire 1F with single pass was completed. You know what it means when I say I'm reducing 400 hours of arcing time? Just for your understanding, a conventional MIG welding machine will draw in close to 20 kilowatts of power, 20 units of power, which means you need to spend 140 rupees for every hour you're welding actually. If you're reducing 400 hours, look at the cost you're going to reduce on the manufacturing cost actually. This is good for industry people. I'm just explaining you to know the effect of reducing the arcing time. Here you can see 7 passes were reduced to 1 pass, which will means they have reduced the welding consumable cost because they moved from flux core arc welding, which is a expensive wire, to a conventional solid wire. They moved from they reduced arc for 6 passes, which means the operator time is saved, the welding power is saved, and your productivity is increased. So that's the benefit of hybrid MIG welding process. It's been used in steel bridging applications also in a big way. So that finished my presentation. I just wanted to touch upon hybrid laser welding, hybrid strip cladding, and also on hybrid MIG welding applications. And if you have any specific questions, I'll be happy to address that.
Participants, so you can ask questions now. Press open. If you have any questions, you can ask or you can type in the chat box. Any questions from the participant side?
That means either I have given a very good presentation or I am not able. Okay.
Sorry,
I'm very sure this is not the best, so I obviously want some questions to come up, please, sir.
Yes, sir. There is a question in the chat box. I will read, sir.
Please.
What about the feasibility of these?
Yeah, I can.
Yes, sir, please.
Feasibility of this process in on-site welding. So which process you're talking about? If you're talking about the hybrid MIG welding, there's a twin wire welding, it is possible. But hybrid laser welding is not possible, and hybrid strip clad is not possible on-site. Only a hybrid twin wire system is, or the twin wire MIG GMW process, you can do it with on-site welding actually. The laser welding will require controlled environment. The strip cladding is not an on-site work; it is more of a shop kind of welding application. But twin wire GMW hybrid welding process, yes, you can do it at site.
Any other questions? So, sir, I think there is no more questions from the participant side.
Okay,
yes,
then I would like to thank you for this opportunity, and also specifically thank to Dr. Murugan for inviting me, and to the organizers, and to you, sir, and also to the attendees. Thank you very much. I'll just share you once again my email ID.
Yes, sir.
If
Yes,
at all you want to ask anything later, you can mail me.
Yes.
I'll be happy to.
Yes, sir. Thank you so much, sir.
not just related to the hybrid part of it, but anything related to welding, you can write to us and we'll be happy to support you, sir. Thank you, sir.
Thank you, sir. Thank you, Mr. Nibin, sir. We are grateful for the time and the effort you took to share your thoughts and experience on hybrid welding. It was really interesting. So thank you so much on behalf of our department and on behalf of our COE welding. We thank you a lot. So thank you, everyone. So we appreciate you being here. So now we can break for a lunch, and we'll meet you again at 2 p.m. exactly.